We now move on to look at the losses that are associated with normal shock waves. We use the term loss here to indicate a loss of the ability to extract work from the gas. This usually implies an increase in the entropy of the gas. And that's what we have when a flow passes through a normal shock wave. Its entropy increases. We'll show that this is the case in the next video, but we'll set the scene in this video by looking at what happens to the stagnation pressure of a gas as it's processed by a normal shock wave. Our analysis and calculations will show that the stagnation pressure always decreases across a shock wave. In the next video, we'll go on to see how we can relate the change in entropy to the change in total pressure and see that the entropy will increase across a shock wave. So here is our normal shock wave again, with flow conditions at state 1 upstream of the shock and state 2 downstream of the wave. Let's find an expression for how the stagnation pressure of the gas changes across the shock. Now, let's imagine slowing down the speed of the gas upstream of the shock wave. But let's do this via an isentropic process. And let's bring the gas to rest. That is, let's stagnate the gas. P01 is the stagnation pressure of the gas at condition 1. In section 2 of the course on isentropic flow, you found that you could determine the stagnation pressure if you knew the static pressure, the Mach number, and the ratio of specific heats. This is the result. You'll recognise the familiar term 1 plus gamma minus 1 over 2 m squared. Now imagine doing the same thing to the flow downstream of the shock. Bring it to rest through an isentropic process. We'll get a similar expression for P02, but with P2 and M2 instead of P1 and M1. So now we have expressions for the stagnation pressures upstream and downstream of the shock wave. If we want an expression for the ratio of the stagnation pressure across the shock, say P02 over P01, we can divide the second expression by the first. And we end up with this. We see the ratio of the static pressure across the shock coming in here. And we had an expression for that from the last component, and it only depends on M1 and gamma. So we should be able to put that in for P2 over P1. We also see M2 coming in here. And we had an expression for that from the last component also. Again, this expression only has M1 and gamma in it. So we should be able to put our expressions for P2 over P1 and for M2 squared in here and get a result that will have the total pressure depending only on M1 and gamma. You might like to pause the video now, get a piece of paper, put in the expressions for P2 over P1 and for M2 and see if you can find an expression for the stagnation pressure ratio. Hopefully you ended up with something like this. You may need to do some simplification of the equations to obtain the stagnation pressure ratio in this form. Let's look at some results from this. Here is the stagnation pressure ratio across a normal shock wave plotted as a function of Mach number for a ratio of specific heats of 1.4. The Mach number is ranging from 1 to 10 and the stagnation pressure ratio is ranging from 0 to 1.2. The first point to note is that the stagnation pressure always decreases across a shock wave. For weak shock waves, that's when the Mach number upstream of the shock is near 1, the drop in stagnation pressure is small. However, you can see that we get a really large loss in stagnation pressure when the Mach number gets high. We need to look at this pressure drop on a logarithmic scale so that we can see what happens at high Mach numbers. This plot shows the stagnation pressure ratio ranging from 0.001 to 1 on a logarithmic scale. You can see that for gamma equals 1.4, the ratio is 0.1 when the Mach number upstream of the shock is around 4.4. So we lose 90% of our stagnation pressure across a normal shock wave at that Mach number. And therefore, for all hypersonic Mach numbers, we'll lose more than 90% of the stagnation pressure. At about Mach 7.7, we lose 99% of the stagnation pressure across a shock. So for high Mach numbers, we get a large loss of stagnation pressure across a normal shock wave. There's one more point about shock waves that I want to make before we finish this video. What happens to the stagnation temperature across a shock wave? I said right at the start of the analysis of the Rankine-Hugoniot relations that we assumed the flow to be adiabatic and that there was no work done on or by the gas as it passed through the shock. So there's no heat transfer and no change in the stagnation enthalpy of the gas. Remember that we're relating enthalpy directly to temperature for our calorically perfect gas. That is, H0, the stagnation enthalpy, is equal to Cp times T0, the stagnation temperature. So if the stagnation enthalpy remains unchanged across a shock wave, so does the stagnation temperature. Therefore, we can say that there's no change in the stagnation temperature of a gas as it passes through a normal shock wave. We can write this as T01, the stagnation temperature upstream of a shock wave, is equal to T02, the stagnation temperature downstream of the shock. In the next video, we'll move on to see how we can use the result we derive for the drop in stagnation pressure across a shock wave to show that the entropy always increases across a shock.